We will begin Unit 4 with the study of rotational motion. If you are familiar with record players in the olden days, you have a turntable on which you have a record player rotating. Well, the rotation is similar to the rotation of this disc. I can rotate this disc. Now you notice that when this disc rotates, every point on the disc is actually doing circular motion. Is that right? A point where I'm touching now, when the disc rotates once, that point describes a circle. In other words, everything that we discussed in connection with circular motion are going to be useful in discussing rotational motion. So let's start by reviewing some of the things that we discussed in circular motion. All right. Here I have the picture of a rotating disc. I have placed the bunny at one point so that when the disc rotates, you can see how the bunny moves. A is the point on the edge of the disc, and OA is the radius of the disc. And I have placed the bunny at the point A so that when the disc rotates, the bunny will go round. See that? As the disc rotates, the bunny will go round. So the rotation of the disc can be studied by looking at the motion of our little bunny. The bunny is initially at point A, and after a time delta t, it will be at point B. Well, you cannot read this there, I'm sure. That is point B. If I may write there, that is my point B. All right. Now, in doing so, what has the radius? What happened to the radius? OB is now the new radius. Again, that is my B. Now, what happens? The radius OA has rotated to the position OB, describing an angle theta. We talked about all this in circular motion. Theta is called the angular displacement of the bunny, and this angular displacement happened in a time delta t. Well, we have done this in circular motion, a relation between linear speed and angular velocity. Now, the rate of change of angular displacement of the rotating object is called the angular velocity. So what is the angular velocity of the bunny? The bunny described an angle theta in a time delta t. Therefore, omega equal to delta theta divided by delta t. Now, what is the unit of measuring omega? It is measured in radian per second, and you also know that radian is a dimensionless quantity. The bunny traveled a linear distance equal to length of this arc. Is that right? And that length AB equal to r theta. Again, we discussed that in circular motion. The length of the arc equal to the radius times theta. That means the bunny traveled a linear distance AB equal to r theta in this distance during this time delta t. Therefore, what is the linear speed of the bunny? The linear speed of v is the length of the arc AB divided by delta t. And that will be r theta divided by delta t, which is r times theta over delta t. But delta theta over delta t, or theta over delta t, is omega. So V equal to r omega. the linear speed of the bunny as it goes around the disk equal to the radius times the angular velocity. Now, let me ask you this. Now, I have placed the bunny at the outer edge of the disk. If I place the bunny somewhere towards the center, somewhere here where I'm pointing, will the angular velocity change? Will the angular velocity of the bunny be different if the bunny was sitting closer to the center? Well, no. Why not? Because the rate at which the radius describes the angle does not change. The bunny can sit anywhere on that radius. The angular velocity will not change. But its linear speed will change. Why? Well, when it is at the outer edge, in order to cover a large distance, it has to go faster. But if the bunny is sitting close to the center, it is now describing a smaller circle. Its linear speed will be lower. So the linear speed depends on where the bunny is sitting. But the angular velocity does not depend on where the bunny is sitting. What that means is the angular velocity is the angular velocity of the disk. Every point on the disk has the same angular velocity. I want you to distinguish there. Every point on the disk has the same angular velocity. You see that? Every point on the disk describes a given angle at the same time. But the linear speed of each particle will be different depending on how far from the center that particle is. The linear speed equal to r omega. Okay, let's do a small problem. A runner running at a constant pace gets halfway around a circular track that has a diameter of 500 meters in 2.5 minutes. In other words, the distance, the linear distance traveled, you can calculate in that time. What are the runner's angular speed and tangential speed? What is the meaning of the tangential speed? Tangential speed is the linear speed. Why is it called the tangential speed? Because the direction of that velocity will be always along the tangent. Alright, now here is this circular track and there I have the runner. Now the runner runs at a constant pace and gets halfway around the circular track. Alright, the radius of the track is, if the diameter of the track is 500 meters, its radius will be 500 divided by 2, that is 250 meters. And the time taken by the runner to go halfway through the track is 2.5 minutes, that is 150 seconds. Now, when the runner is halfway around the circle, tell me, what is the angular displacement of the runner? Well, if the runner goes round the circuit completely once, the angular displacement will be 2 pi radians. When the runner goes halfway through, the angular displacement will be pi radians. There it's going over here. The runner has described an angle of pi radians. And this pi radians is described in a time 150 seconds. Therefore, omega, the angular velocity, is delta theta divided by delta t, the rate of change of angular displacement. That is pi radians divided by 150 seconds. That is 0.021 radian per second. if you know omega, can you now find the tangential speed, the linear speed? Well, V equal to R omega, where R is the radius. We now know omega, therefore the linear speed is 5.2 meter per second. The runner is a very fast runner. Okay, let's do another one. The disc on the right has a radius 15 centimeter and it makes 12 revolutions every 5 seconds. What is the angular velocity of the disc? What is the linear speed of the bunny sitting at the edge of the disc? Well, we need to find the angular velocity. To find the angular velocity, what are the information you need? The angular displacement and the time taken for that angular displacement. Well, before I write down, we can think about it. Look at this, we are given the time 5 seconds. Can you tell me what is the angular displacement that happened during that 5 seconds? In 5 seconds, the disc made 12 revolutions. What is the angular displacement for 1 revolution? When the disc makes 1 revolution, the angular displacement is 2 pi radians. Therefore, when the disc makes 12 revolutions, the angular displacement is 12 times 2 pi, that is 24 radians. So, the angular displacement for 1 revolution is 2 pi radians, and therefore the angle described for 12 revolutions is 24 radians. And to describe this angle, the time taken is 5 seconds. Therefore, angular velocity is delta theta divided by delta t. 24 radians divided by 5 seconds, that is 4.8 pi radians per second. And now, what is the linear speed of the bunny? The bunny is sitting at the edge. That means the distance, the radius of the bunny's circular track is 15 centimeter. Therefore, V equal to R omega. If V is the linear speed of the bunny, then V equal to R omega. So V equal to R omega gives you V equal to 2.26 meter per second. You can see all these are review from circular motion. There is no new materials here. Now, radian does not appear in the calculations because radian is a dimensionless quantity. Now, one thing again I want to reiterate, the linear speed of the bunny will depend on the distance of the bunny from the center. In other words, the radius of revolution. But the angular velocity does not change. No matter where the bunny is sitting, the angular velocity will be the same, namely omega. Okay, let's now review one more time the concept of frequency and period. I'm sure you remember this concept. Frequency, the number of rotations per second of a rotating object is called frequency. And frequency is measured in hertz, which is per second. If the bunny makes 12 revolutions in 5 seconds, alright, I made it go 12 times in 5 seconds, then the frequency is 12 divided by 5 hertz. And the time taken for the bunny to go around once, or the time taken by any rotating object to go around once, is called the period. So, if the bunny makes 12 revolutions in 5 seconds, then what is the period? The time taken for one revolution is the time taken for 12 revolutions divided by 12. 5 seconds divided 5 revolutions divided by 12 seconds will be the period. Okay. Now, notice here that the period is the reciprocal of the frequency. We talked about all that earlier. So, during the period t, the angle described is 2 pi radians. Is that right? During the period means the time taken to go around once. What is the angular displacement during one period? It's 2 pi radians. Therefore, you can say omega equal to angular displacement divided by the time. When the angular displacement is 2 pi radians, the time is 1 period. So omega equal to 2 pi divided by the period. Let me reiterate it. That is a very important relation and you cannot forget it. We talked about it in circular motion. Can you tell me, can you give me the equation in terms of the frequency? Omega equal to 2 pi divided by the period, which is the same as 2 pi multiplied by the frequency. Okay. A simple problem. What is the period of revolution of a 33.3 RPM record? I don't think many of you would remember we used to have these 33.3 RPM records, which used to hold 6 songs on one side, altogether 12. Now what does 33.3 RPM means? 33.3 revolutions per minute. Alright? The question here is, what is the period of a 33.3 RPM? If a disc makes 33.3 revolutions in 1 minute, what is the time taken to go around once? You see? The time taken for 33.3 revolutions is 1 minute. What is the time taken for one revolution? It is 1 minute, which is 60 seconds, divided by 33.3. Is that right? So 33.3 RPM is 33.3 divided by 60 revolutions per second. If the disc makes 33.3 revolutions in 60 seconds, then the period is 33.3 over 60 revolutions in 1 second. Is that right? That's right. Now that will be 0.56 hertz. And that is the frequency. You see? It makes 33.3 revolutions in 1 minute. Means it makes 33.3 over 60 revolutions in 1 second. The number of revolutions in 1 second is what we call the period. The frequency. Now we have the frequency. Can you find the period? The period is the reciprocal of the frequency. So T equal to 1 over F. That will be 1 over 0.56. That is 1.79 seconds. Alright, what is the same quantity? What is the period of a 45 RPM? In the same way, 45 RPM, it used to be a smaller record, 45 RPM. 45 RPM means 45 revolutions in 1 minute. Therefore, it is 45 divided by 60 revolutions in 1 second. And that is 0.75 hertz. Therefore, the period is 1 over the frequency, 1 over 0.75, that is 1.33 seconds. Okay, another one. We will now discuss the concept of angular acceleration. If a disk is rotating at uniform angular velocity, the rate at which the angle changes will remain a constant. We will say the angular velocity is uniform. But very often we don't come across rotations that happen uniformly. Very often we come across disks that are set into rotation. Now you can see the disk is not rotating now. If I set this into rotation, its angular velocity is going to increase from 0 to some value. That means the angular velocity is changing. If the angular velocity changes, it means there is angular acceleration. So if the angular velocity keep on changing, then you have angular acceleration. You now see the rotating disk stopped. If the rotating disk is stopping, its angular velocity decreases from a high value to 0. So when the disk begins to rotate, it picks up angular speed, angular velocity. The angular acceleration will be positive. When the disk slows down and comes to a stop, the angular velocity decreases from a large value to 0. The angular acceleration will be negative. Well, let's now talk about the angular acceleration of a rotating disk. We will represent angular acceleration of a rotating object by alpha. So you can see we are using English alphabets for linear motion and Greek alphabet for rotational motion, right? V for linear velocity, omega for angular velocity, A for linear acceleration, alpha for angular acceleration. All right? So angular acceleration alpha is the rate of change of angular velocity omega. In other words, we can define angular acceleration the same way we define linear acceleration. So alpha equal to delta omega divided by delta t. The change in angular velocity divided by the time. And what is the unit for measuring alpha? The unit for angular velocity is radian per second. Divide that by second, you get radian per second squared is the unit for angular acceleration. Well, delta omega, if omega 0 is the initial velocity and omega f is the final velocity, then delta omega will be omega f minus omega 0. So angular acceleration results in an increase or decrease in the speed of rotation. If the rotation gets speeded up, angular acceleration is positive, and it slows down to 0, the angular acceleration is negative. If omega 0 is the initial angular velocity of a rotating object and omega f its angular velocity after a time t, then alpha can be written as omega f minus omega 0 divided by t, and this is the same definition we have for linear velocity or linear acceleration. A equal to Vf minus V0 over t, right? Now, a change in the speed of rotation means that there is a tangential acceleration. You see, the only way you can change the speed of rotation is to change the linear speed of every point on the object. You see, if I want to increase the speed of rotation of this disk, a point on that disk is going to move faster when the angular velocity increases. That means an increase in the angular velocity results in an increase in the linear speed of the object, of every point on the object. That means a change in the speed of rotation means that there is a tangential acceleration. That means there is a linear acceleration for every point on the object that rotates. I hope you understand that. We can obtain a relation between angular acceleration alpha and tangential acceleration A by using the relation V equal to R omega. Well, this is the relation between linear speed and angular velocity. We can now use this to obtain a relation between linear acceleration A and angular acceleration alpha. Well, you can look at this and tell me what that relation is. Well, the definition of linear acceleration is the rate of change of linear velocity, A equal to delta V divided by delta T. And let's replace this V by R omega. So delta V becomes delta of R omega, the change in the linear velocity, divided by delta T. And I can now take that R outside. If the radius is a constant, I can write it as R times delta omega divided by delta T. Now tell me, what is delta omega divided by delta T? Delta omega divided by delta T is the rate of change of angular velocity with time, which is angular acceleration. So that will be R alpha. So linear acceleration equal to R times the angular acceleration. In the same way as linear velocity equal to R times angular velocity. So these relations are important. We will be using them as we go on. V equal to R omega, A equal to R alpha. Okay, let's do a problem. A turntable set for 45 RPM is turned on and reaches its operating speed in 1.25 seconds. What is the average angular acceleration of the turntable? Well, I'm sure some of you at least know what a turntable is. A disc that rotates. When you turn it on, the moment you turn it on, its initial angular velocity is 0. It picks up angular velocity and it reaches the operating speed. What is the operating speed? Is 45 RPM. So we have initial angular velocity omega 0 equal to 0. The final angular velocity, you can see 45 RPM is actually the angular velocity, revolutions per second. You need to convert it to radian per second. How do you convert revolutions per minute? Not revolutions per second. This is revolutions per minute. How do you convert that to radian per second? You see, each revolution is 2 pi radians. So 45 revolutions is 45 times 2 pi radians. That will be 45 times 2 pi radians per minute, which is 45 times 2 pi radians divided by 60 radians per second. So 45 RPM is 45 times 2 pi divided by 60 radian per second. In other words, 45 revolutions is 45 times 2 pi radians, and so many radians are described in 1 minute, which is 60 seconds. Therefore, 45 RPM is the same as 45 times 2 pi divided by 60 radian per second. To convert revolutions per minute to radian per second, multiply by 2 pi divided by 60. And that is 4.7 radian per second. So the turntable changes its angular velocity from 0 to 4.7 radian per second in this time of 1.2 seconds. Therefore, alpha equal to omega f minus omega 0 divided by t. That will be 4.7 minus 0 divided by 1.25 seconds. That is 3.8 radian per second squared is the angular acceleration. Alright, let's now look at equations of rotational motion. Well, you know your equations of linear motion, don't you? What are the equations of linear motion? We've got Vf equal to V0 plus At, one equation. What's the second equation? X equal to x0 plus V0t plus 1/2 At squared. The second equation. The third equation is Vf squared equal to V0 squared plus V0 squared plus 2ax. You can actually translate those equations for linear motion to describe rotational motion by replacing linear velocity by angular velocity, linear acceleration by angular acceleration, and linear displacement by angular displacement. Now, you can see here, linear velocity is v. So let me say linear and rotational. Linear velocity is v, rotational velocity is omega. Linear acceleration is a, rotational acceleration is alpha. Linear displacement we generally call x or y and so on. The rotational displacement is theta. So, what all you need to do is write down the equations for linear motion and replace your v by omega, a by alpha, x by theta. You have your equations for rotational motion. Let's do that. Now, we can write corresponding equations for rotational motion by replacing v by omega, a by alpha, and x by theta. Alright, let's write those equations. Linear equations. We've got v equal to v0 plus at. In place of vf, I simply wrote v, velocity at any given time. Tell me, what is the corresponding rotational equation? Well, simple, replace v by omega, a by alpha. We get omega equal to omega 0 plus alpha t. Alright, the second rotational equation, x equal to x0 plus v0t plus 1/2 at squared. X will be replaced by theta, v0 by omega 0, and a by alpha. We got theta equal to theta 0 plus omega 0t plus 1/2 alpha t squared is the second rotational equation. What is the third linear equation? v squared equal to v0 squared plus 2ax, and in rotation it becomes omega squared equal to omega 0 squared plus 2 alpha theta. You can see I have used here omega for omega f, v for vf. Okay, we can now use these rotational equations to solve problems. Let's do a small problem. A 33.3 RPM record on a turntable uniformly reaches its operating speed in 2.45 seconds once the record player is turned on. What is the angular displacement during this time? What is the number of revolutions of the disc during this time? What is the corresponding arc length on the circumference of the 15 centimeter diameter record? Alright, first of all we need to find the angular displacement. Well, that means we need to find the angular acceleration. So let's pick our data. Initial angular velocity omega I equal to 0. T is 2.45 seconds. The radius of the disk is 0.075 second. Is that right? Yes. 15 centimeter is the diameter. That means its radius is 7.5 centimeter, which is 0.075 meter. Well, what is the final omega? It reaches the operating speed. What is the operating speed? 33.3 RPM. This is the final angular velocity. Initial angular velocity is 0. In 2.45 seconds, it reaches the operating speed of 33.3 revolutions per minute. Convert revolutions per minute to radians per second. Multiply by 2 pi and divide by 60. So that will be 3.5 radian per second. Now you can use these values to find alpha. Alpha equal to omega f minus omega 0 divided by t. That will be 3.5 minus 0 divided by 2.45 seconds. That is 1.43 radian per second squared is the angular acceleration. Well, we know the angular acceleration. We know the initial angular velocity. We know the time. Can you calculate the angular displacement during that time? What is the equation we will use? Well, this is the equation for angular displacement. Theta equal to theta 0 plus omega 0 t plus 1/2 alpha t squared. Theta 0 is 0. Omega 0 is 0, therefore theta equal to 1/2, alpha is 1.43, t is 2.45 seconds. So that will be 4.29 radian. The angular displacement is 4.29 radian. What is it that we want next? What is the number of revolutions of the record during this time? How many times did the record go round during this time? Well, you know that if the record goes round once, the angular displacement will be 2 pi radians. That means there are 2 pi radians in one revolution. And you know that the disk rotated through 4.29 radians during that time. Now, this 4.29 radians correspond to how many revolutions? 1 revolution corresponds to 2 pi radians. Therefore, 4.29 radian will correspond to 4.29 divided by 2 pi number of revolutions. So the number of revolutions is the angular displacement divided by 2 pi. I hope you understand that, because each revolution is 2 pi radians. Therefore, an angular displacement of theta will correspond to theta divided by 2 pi revolutions. That will be 4.29 radian divided by 2 pi radian, which is 0.68. So the disk went through not completely 1 revolution. It completed 0.68 of a revolution. How about the last part? What is the corresponding arc length on the circumference of a 15 centimeter diameter rocoid? Well, what is the relation between arc length and the angular displacement? Well, what happened here is the disk went through, described an angular displacement of how much? We got theta equal to 4.29 and the radius is 0.075 meter. You see, the disk rotated through an angle of 4.29 radians, and therefore the linear displacement, the displacement along the arc, the corresponding arc length equal to a radius times the angle, arc length equal to r theta. Alright, so that gives us, if delta s is the arc length, then delta s equal to r times theta. R is 0.075 meter, theta is 4.29 radian. Therefore, the length of the arc for that revolution is 0.32 meter. Okay, another one. When a turntable rotating at 45 RPM is turned off, it comes to rest in 15 seconds. Find A, the angular acceleration, the average angular velocity of the turntable, and the number of revolutions it makes before stopping. A similar kind of problem. What do we have? A turntable is rotating at 45 RPM. That is, the initial angular velocity is 45 RPM. Convert that to radian per second. What do? Multiply by 2 pi and divide by 60. That will be 45 multiplied by 2 pi radians divided by 60 seconds. That is 4.7 radian per second. And what's omega f? What is the final angular velocity? Is 0. It is brought to a stop. And it happened in a time t equal to 15 seconds. Therefore, angular acceleration is omega f minus omega 0 divided by delta t. That is 0 minus 4.7 radian divided by 15 seconds. That is negative 0.31 radian per second squared. When a rotating disk comes to a stop, its angular acceleration is negative. What is the average angular velocity of the turntable? How do you find the average velocity? If you know the initial velocity, and the final velocity, the average velocity is the final velocity plus the initial velocity divided by 2. That will be 4.7 radian per second plus 0 divided by 2, that is 2.35 radian per second, is the average velocity during that time. And now, what is the number of revolutions it makes before stopping? Well, to find the number of revolutions, you need to find the angular displacement. How do you find the angular displacement? Well, theta equal to theta 0 plus omega 0 t plus 1/2 alpha t squared. Theta 0 is 0. Omega 0 is 4.7 radian per second. And alpha we calculated, I didn't carry it here, but we have that value in the previous slide. Well, so omega 0 is 0. Theta 0 is 0. Omega 0 is 4.7 radian per second times t is 15 seconds plus 1/2 alpha. We calculated the angular acceleration as negative 0.31 radian per second squared times t squared is 15 squared. Calculate this on your own on your calculator. That should give you 35.6 radians. The angular displacement of the disk in coming to a stop is 35.6 radians. Now, this 35.6 radians correspond to how many revolutions? Each revolution is 2 pi radians. Therefore, the number of revolutions in coming to a stop will be this divided by 2 pi. So number of revolutions is theta divided by 2 pi. That is 35.6 divided by 2 pi, and that is 5.7. The disk did 5.7 revolutions in coming to a stop. Another one. Starting from rest, a disk takes 10 revolutions to reach an angular velocity of 8 pi radian per second. How many additional revolutions are required for the disk to double its angular velocity to 16 pi radian per second? Now understand this problem very well. Read it one more time. We have a disk is starting from rest and it takes 10 revolutions to reach this angular velocity 8 pi radian per second. Now 10 revolutions means how many radians? 20 pi radians. Now the question is, how many additional revolutions are required for the disk to double its angular velocity to 16 pi radians? Alright, what do? First we find the angular acceleration alpha using the first situation. Now what are the data there? We have omega 0 equal to 0. The disk starts from rest and it acquires an angular velocity of 8 pi radians. Omega f equal to 8 pi radians. In describing an angle, how much angles? 10 revolutions is 10 times 2 pi radians. That is 62.83 radians. So look at that data once again. A disk starts from rest and in rotating through an angular displacement of 62.83 radian, it attains a final angular velocity of 8 pi radians per second. So we have the initial angular velocity, final angular velocity, and the angular displacement. Can you use these values to find the angular acceleration? What is the equation you will use for that? Remember, the equation you will be using will be the one that does not contain time. Alright? We use the equation omega f squared equal to omega 0 squared plus 2 alpha theta. That will be omega f is 8 pi. 8 pi squared is omega 0 is 0 plus 2 alpha theta. Theta is 62.8. And you can now solve for alpha from here. I'm going to leave it for you to do that on your own. I got alpha equal to 5.03 radian per second squared. And now, what you need to understand is that the angular acceleration is not changing. This angular acceleration is a constant. So, we need to now find how many additional revolutions. In order to do that, we will find the total angular displacement for it to reach that final angular velocity. So, for the next part, what is for the next part? In the next part, our final angular velocity is 16 pi radian per second. The initial angular velocity, you see, we have now completed the first part. The disk has an angular velocity of 8 pi radian per second. Now from 8 pi, its angular velocity is going to increase to 16 pi. So we will say omega 0 is 8 pi, omega f is 16 pi, and angular acceleration is 5.03 radian per second squared. We got the initial angular velocity, final angular velocity, and alpha. Can you find the angular displacement during that second part? Yes, we can find the angular displacement using the same equation. Omega f squared equal to omega 0 squared plus 2 alpha theta. Well, replace these values. That will be 16 pi all squared equal to 8 pi all squared plus 2 alpha theta. We can now solve for theta. And solving for theta gives, I want you to do this on your own. It will be this quantity minus this. Evaluate that first. And then divide it by 2 times 5.03. And that gives me theta equal to 188.4 radian. Now, this is the additional angular displacement from 8 pi radian per second to 16 pi radian per second. And we want to find how many additional revolutions. 188.4 radian correspond to how many revolutions? So the additional revolutions will be this radians divided by 2 pi, and that is 30 additional revolutions. So in 30 additional revolutions, the angular velocity will become double the value. Another example. A Ferris wheel of radius 12 meter rotates once in 35 seconds. It goes round once in 35 seconds. What is its angular velocity in radian per second? What is the linear speed of a passenger? What is the centripetal acceleration of a passenger? Well, here is the Ferris wheel. You are familiar with this. The radius is 12 meter, that's that distance, and passengers are sitting at the edge. Means the distance of a passenger from the center is 12 meter. And the period is 35 seconds. The time taken to go round once is 35 seconds. Well, you know that omega equal to 2 pi divided by the period. Now look at that equation, how handy that is. The angular velocity is 2 pi divided by the period. That is 2 pi divided by 35 seconds. That is 0.18 radian per second. So you can see the first part is so simple. How about the second part? What is the linear speed of a passenger? If a passenger is sitting here, the linear speed is the same as the tangential speed, v equal to r omega, where r is 12 meter, omega is 0.18 radian per second, and that will be 2.16 meter per second. And the next one, what is the centripetal acceleration? Do you remember the equation for centripetal acceleration? We have that equation using linear speed and also the angular velocity. Well, the centripetal acceleration is given by A equal to v squared over r. We just calculated v. That will be 2.16 squared over 12. That is 0.39 meter per second squared. And that is the centripetal acceleration of the passenger. That means the passenger will be experiencing a force towards the center with this acceleration. Well, I think what we have, well, why not do one more problem before we close the lesson? A bicycle wheel has a diameter of 1.2 meter. The bicycle accelerates from rest to a velocity of 22 km per hour in 10 seconds. A. What is the angular acceleration of the bicycle? B. What is the number of revolutions of the wheel during this time? And C. What is the distance traveled by the cycle during this time? Well, all these we have actually done already. This is a recap of what we have already done. Now I have a fancy bicycle wheel here. What is given to us? The diameter of the wheel is 1.2 meter, means the radius of the wheel is 0.6 meter. The initial velocity is 0. The final velocity is 22 km per hour. The bicycle accelerates from rest, v0 equal to 0, to a velocity of 22 km per hour. Convert 22 km per hour to meter per second. Divide by 3.6. That is 6.1 meter per second. And this happened during a time t equal to 10 seconds. Well, we can now calculate the linear acceleration of the cycle. Is that right? By using this equation. Vf equal to v0 plus 80. Therefore, 6.1 equal to 0 plus 10a, or acceleration is 0.61 meter per second squared. If this is the linear acceleration, what is the angular acceleration of the bicycle wheel? The bicycle wheel has a radius of 0.6 meter and the linear acceleration is 0.61 meter per second squared. Remember, A equal to R alpha. Therefore, alpha equal to A over R. Angular acceleration is linear acceleration divided by the radius. That is 0.61 meter per second squared divided by 0.6 meter. That is 1 radian per second squared is the angular acceleration. C. What is the distance traveled by the cycle during this period? No. B. What is the number of revolutions of the wheel during this period? What is the number of revolutions? To find the number of revolutions, we find the total angular displacement using theta equal to theta 0 plus omega 0 t plus 1/2 alpha t squared. Theta 0, of course, is 0. Omega 0 is 0. If V0 is 0, then omega 0 is 0. Alpha we just calculated. Therefore, theta equal to 0 plus 0 plus 1/2 alpha is 1. T squared is 10 squared. That is 50 radians. So the angular displacement is 50 radians. Can you convert that to revolutions? Each revolution contains 2 pi radians. Therefore, 50 radians will be equivalent to 50 divided by 2 pi revolutions. That's approximately 8 revolutions. All right, what's the next one? What is the distance traveled by the cycle during this period? Now remember, the distance traveled by the cycle is the length of the arc. When the wheel completes 1 revolution, the length of the arc is 2 pi r, and that is the distance the bicycle wheel will be advancing forward. For each revolution of the wheel, the bicycle advances by 2 pi r, the circumference of the wheel. Is that right? And therefore, what is the total distance advanced for 8 revolutions? That will be 8 times 2 pi r. That will be 30.2 meter. Well, I think we have done enough number of problems in studying rotational motion. Now, this is actually the foundation for rotational motion. We have to now look at the cause of rotational motion. You see, you know the cause for linear acceleration, don't you? It's a net force. And so, in our next lesson, we will be asking the question, what is the cause of a rotational acceleration? So, we will take up rotational motion for further investigation in our next lesson. All right, I will see you for that after some time.